Alrighty, method students, welcome back to school. Hope everyone is well. Today we're doing this quick finish off with chapter number 9, looking at when a function is differentiable. Now, as you can read there, a function of f is said to be differentiable at x equals a if the limit as h approaches 0 for that there exists. So that's useful to know. That's in the bubble box down the bottom, which is worthwhile making a note of. As we've looked at before earlier in the chapter, often we are just calculating the derivative of them given their implicit domains. However, that's not true for all of the functions. So earlier in 9D we had this hybrid function. Yeah, they call them piecewise functions. I still call them hybrid functions, whereby you can see here if you have part of it where it's greater than or equal to 0, we've got x, and here it's a negative x. If you were to calculate the gradient of each of those, obviously the gradient when it's greater than or equal to 0 would be 1, so to the right would be 1, and here it would be negative 1 to the left of 0. So again, if you consider if you sketched the graph of the derivative function, obviously to the left of 0 you'd have negative 1, and then to the right of 0 you would have 1, and obviously they are not joined there. So at that particular point, at x equals 0, where there is the gap, and the graph, obviously it's not continuous and it's not differentiable at that particular point. So it says here, it was shown in the previous section that some hybrid functions are continuous everywhere. Yep. And so it says sometimes some hybrid functions are differentiable everywhere. Cool. And ultimately, it's the smoothness of the join that determines whether this is the case. So again, when you get these and you're looking at whether there's a gap or whether there's a smooth transition between each of them, will determine whether it's differentiable. So let's have a look here. Example 45. We've got the hybrid function, so greater than 0 is obviously this quadratic bit. Here we've got the linear part when it's less than 0. If you had to sketch the derivative f dashed x, it's obviously going to be these parts. That's the derivative of that, that's the derivative of that. Yep, and you can see to the left of 0, so less than 0, it's going to be just a straight line, 2, and here where it's greater than or equal to 0, we've got the straight line going up for 2x plus 2. Cool. And in this particular case, you can see that when the derivative is equal to 0, it's actually defined and it's equal to 2. You should be able to see that there quite well. It's where that cuts the axes. So in this particular case, two sections of the graph join smoothly. There's no jump or gap. You don't have to take your pen off the page. So it is able to be differentiated. Yep, it's differentiable at that particular point, 0, 1. Cool. On the other hand, let's have a look here. You've got the function. Again, we've got a quadratic, except this time we've got the linear here. Sketching the derivative of that, obviously you've got the 2x plus 2 bit when it's less than 0. Sorry, when it's greater than 0. So you can see here, notice it's not greater than or equal to, so it's the open circle there as well. To the left of 0, so less than 0, it's just 1, it's a straight line. Again, open circle here. Now at that particular point, if you were to try and work out f dash of 0, then it's not possible, because if you were to calculate the limit as we approach from the left hand side, that is different than the limit as we approach from the right hand side. They're not equal, they're not the same as each other. So at that particular point, at 0, you can't differentiate it. So what you could say is this function is differentiable for all real values except at 0. Yeah. Alrighty, this is important. It says if a function is differentiable at x equals 0, x equals a, then it's also continuous at x equals a. Happy days. If it's differentiable at x equals a, then it's continuous at x equals a. Aha, but on the other hand, the following is not true. Yep. So it says here, if you have something that is continuous at x equals 0, and as we get the limit as x approaches 0 for that function, But if in this particular case f is not differentiable at x equals 0. So what it's saying is one way is true where you've got both of them, but it can't work back the other way. If it's continuous, it's not necessarily differentiable at that particular point. Yep. Alrighty, let's have a look at this last thing before you guys do some work. We've got this function here, happy days. It says state when the derivative is defined and sketch the graph of the derivative function. Cool. So we can work out the derivative of this function. It's listed here, happy days. If you were to sketch this, clearly you can see it's a truncus, and in this particular case, there is an asymptote at x equals 0. Yep. So again, in this particular case, it's not going to be defined at that particular point, the derivative. Yep, because there is that asymptote there. Happy for you to look at the explanation using first principles, but it's pretty obvious when you sketch it and you can see what's going on there. Here's the section summary, 2 things that we spoke about. Happy days, they can go into your fun notes. Thank you very much for listening. Have a good day. Bye for now.